In this chapter, we will discuss various types of data models. The models we will be discussing can be used for either conceptual data modeling, logical data modeling, or even physical data modeling. We will discuss the models in a chronological order based on when they were developed. Hence, we will start by reviewing legacy data models and then gradually move on to more sophisticated data models. In doing so, we will extensively discuss the expressive power and limitations of each of the models. Let's start with the overview. We will kick off with a brief recapitulation of the basic concepts of data modeling. We will then discuss the hierarchical model, the CODASYL model, the entity relationship model, the enhanced entity relationship model, the relational model, and the Unified Modeling Language or UML model. Developing a conceptual scheme or model is the first step of database design. The goal is to adequately and accurately capture the specifications of the data and constraints to be represented in the database. To do so, both the database designer and end user should closely collaborate. The main focus of conceptual data modeling is to capture the semantics of the business process as accurately as possible without being concerned about DBMS-related issues. Hence, we need a high-level model which allows the database designer to unambiguously capture the data requirements and at the same time provides a user-friendly representation to the end user such that he or she can also accurately understand what has been modeled. In case the model is agreed upon by both parties, it can proceed to the next stage of database design. A very popular conceptual data model is the enhanced entity relationship model, as we will extensively discuss later. We will start by reviewing data models as they have been developed through history. Our motivation to do so is to provide a step-by-step overview and understanding of how different models have evolved in terms of their expressive power. Furthermore, many firms still struggle with legacy DBMS applications which were built using legacy data models. Hence, it is important to also thoroughly understand the working and impact of this. Here you can see the various steps of database design illustrated once more. We start from a business process. Think about a procurement application, invoice handling process, logistics process, or salary administration. An important first step is to carefully understand the various steps and information processed during the process. A database designer and end user will then closely collaborate to write down the data requirements of the process in a conceptual data model. As mentioned before, this should be a high-level model and thus both easy to understand to the business user and formal enough to the database designer. Obviously, this conceptual model will also have its limitations, which should be clearly documented and followed up. Once all parties have agreed on the conceptual model, it can be mapped to a logical data model, which takes into account the implementation environment. In other words, the logical data model is a data model that will be used by the DBMS for actual implementation. In a final step, the logical data model can be mapped to a physical data model, which can then be implemented. During this mapping process, it may be possible that semantics get lost or is added. Again, this should be clearly documented and followed up during application development. The hierarchical model is one of the first data models that was developed. The model originated during the Apollo project conducted by NASA. To manage the huge amounts of data collected, IBM developed the Information Management System, or IMS DBMS. It is purely based on a hierarchical data model. There is no formal description available. It also has lots of structural limitations and is considered to be legacy. The two key building blocks of the hierarchical model are record types and relationship types. A record type is a set of records describing similar entities. Think about a product record type or a supplier record type. A record type has 0, 1, or more records. It consists out of data fields or data items. A product record type has a field product number, a field product name, a field product color, etc. A relationship type connects two record types. More specifically, it models the relationships between record types. Only hierarchical structures are allowed, or in other words, only 1 to n relationship types can be modeled. Hence, a parent record type can have multiple child record types, but a child record type has at most one parent record type. Relationship types can be nested. Hence, a child record type can be parent in another parent-child relationship type, which allows to build hierarchical structures. The root record type is a record type which sits at the top of the hierarchy, whereas a leaf record type sits at the bottom of the hierarchy. You can see this illustrated here. We have a parent record type and a child record type. A parent record can be connected to minimal 0, maximal n child records. Vice versa, a child record can be connected to minimum 1, maximum 1 parent. Hence, a child record is always connected to exactly one parent. No other cardinalities are supported in the hierarchical model, which makes it very restrictive in terms of expressive power. Note that the relationship type is always summarized in terms of its maximum cardinalities. In our case, we can say that the hierarchical model only supports 1 to n relationship types. Here you can see an example. We have 3 record types: department, employee, and project. The department record type has 3 data fields: department number, department name, and department location. The department record type participates in 2 parent-child relationship types. A department can have 0 to n employees. Vice versa, an employee is always connected to one department. A department can work on 0 to n projects. Vice versa, a project is always worked on by exactly one department. This is a very simple hierarchical structure. Department is the root record type, and both employee and project are the leaf record types. In the hierarchical model, all record data needs to be retrieved by navigating down from the root node of the hierarchical structure. In other words, the DML adopted is procedural, which is not that nice. Furthermore, it is also very rigid and thus limited in terms of expressive power, since it only allows 1 to n relationship types. There is no support to model n to m or 1 to 1 relationship types. Hence, these have to be implemented using workarounds. To implement an n to m relationship type, we can assign one record type as the parent and the other as the child record type. In other words, we transform the network structure to a tree structure, which will obviously involve a lot of semantics. Any relationship type attributes, such as number of hours an employee worked on a project, can be put in the child record type. This solution will create redundancy, which is dependent upon both the amount of data in the child record type and the value of the maximum cardinality from the child record type to the parent record type. Let's illustrate this with an example. Let's say we have an N-to-M relationship type between project and employee. Put differently, an employee can work on 0 to N projects, whereas a project can be worked upon by 0 to M employees. To implement this in the hierarchical model, we need to map it to a 1 to N relationship type, which is obviously not ideal. Hence, we can opt to make the project the parent and employee the child record type. Here you can see some example records for this implementation. Project number 10 has 3 employees working on it. Employee 110, Employee 120, and Employee 145. You can also see that Employee 110 works on all 3 projects, Project 10, 15, and 20. Hence, the data of Employee 110 is replicated, which is not nice from both a storage and maintenance perspective. If the data of Employee 110 is updated in one relation, it must also be updated in the other relations or inconsistent data will occur. Note that the number of hours an employee worked on a project can be put in the child record type. Another alternative to implement an N-to-M relationship type is to create 2 hierarchical structures and connect them using a virtual child record type and a virtual parent-child relationship type. Pointers can then be used to navigate between both structures. The relationship type attributes can be put in the virtual child record type. This solution has no more redundancy, since multiple virtual childs can refer to one parent. Let's again illustrate this with an example. Here you can see our earlier N-to-M relationship type between employee and project, but now implemented using virtual child and virtual parent record types. The virtual childs have pointers to virtual parents. Although this solution has no more redundancy, it is clear that it is rather artificial and not so nice to maintain. One-to-one relationship types are a special case of a 1 to N relationship type with N equal to 1. These relationships cannot be supported as such in the hierarchical model. Hence, the application programs should take care of this, which is not nice because we are now forced to include part of the data definitions in our applications, which seriously hampers maintenance and consistency. The hierarchical model only allows relationships of degree 2, or in other words, with 2 participating record types. Recursive relationship types with degree 1, relationship types with more than 2 record types need to be implemented using virtual child record types. Finally, the maximum and minimum cardinality from child to parent is 1. A child can thus not be disconnected from its parent. This implies that once a parent record is removed, then all connected child records will be removed as well, hereby creating an on-delete cascade effect. Here you can see an example of a hierarchical data model for an HR administration business process. It includes 2 hierarchical structures, which are connected. Department is the root record type of the first hierarchy and employee of the second hierarchy. A department can work on 0 to N projects. A project is being worked on by exactly one department. The works on record type is a virtual child to implement the N-to-M relationship type between project and employee. It also includes the hours worked data item, which represents the amount of hours an employee spent working on a project. The manager virtual child record type refers to the employee record type. Note that according to this implementation, a department can have more than one manager. The worksat virtual child models the relationship between department and employee. 0 to n employees can work in a department. The manager's virtual child models a recursive relationship type, which specifies the supervision relationships amongst employees. An employee can manage 0 to n other employees. It is clear that this model is not user-friendly and hard to interpret. It also has various model limitations. More specifically, our model does not allow to guarantee that each department has exactly one manager. According to our model, a department can have 0 managers, or even more than one manager. We can also not enforce that a department has at least one employee. According to our model, it is perfectly possible that a department has 0 employees. Hence, most of these constraints, or rules, have to be directly embedded in the application programs, which is clearly not optimal. The CODASYL model is a next data model developed by the database task group of the Conference on Data System Languages in 1969, so not that much later than the hierarchical model. It has various popular software implementations, such as IDMS from Culinet Software, which was later acquired by Computer Associates and rebranded into CA IDMS. It is an implementation of the network model, which originally includes record types and links and allowed to model one-to-one, one-to-n, and n-to-m relationship types. However, the CODASYL model only includes record types, set types, and one-to-n relationship types. Although this may sound quite familiar to the hierarchical model at first sight, there are some clear differences as we will illustrate. Note that also the CODASYL model is considered to be legacy and has lots of structural limitations. The two key building blocks of the CODASYL model are record types and set types. Just as in the hierarchical model, a record type is a set of records describing similar entities. It has 0, 1, or more records or record occurrences. It consists out of various data items. As an example, supplier record type can have data items such as supplier name, supplier number, etc. The CODASYL model provides support for both vectors and repeated groups. A vector is a multi-valued attribute type or an atomic data item for which a record can have multiple values. For example, if a supplier can have multiple email addresses, then this can be modeled using a vector. A repeated group is a composite data item for which a record can have multiple values or a composite multi-valued attribute type. For example, if a supplier can have multiple addresses, each with their street name, number, zip code, city, and country, then this can be modeled using a repeated group. The support for vectors and repeated groups is already a first difference with the hierarchical model. A set type models a one-to-n relationship type between an owner record type and a member record type. A set type has a set occurrence for each record occurrence of the owner record type together with all member records. Put differently, a set occurrence has one owner record and 0, 1, or more member records. It is important to note that the CODASYL interpretation of a set does not completely correspond to the concept of a set as we know it in mathematics. Remember, in mathematics, a set is defined as a collection with similar elements and without ordering. However, A CODASYL set has both owner and member records, and it is also possible to order the member records. Here you can see a set type with the corresponding cardinalities. An owner record can be connected to minimum 0, maximum n member records. Vice versa, a member record can be connected to minimum 0, maximum 1 owner records. Hence, a member record can exist without being connected to an owner record. This is another key difference with the hierarchical model. Here you can see a summary of the differences with the hierarchical model. As we already mentioned, the support for vectors and repeated groups is new in the CODASYL model. Members can also be disconnected from their owner, since the minimum cardinality from member to owner equals 0. Furthermore, a record type can be member record type in multiple set types, which allows the creation of network structures. In a hierarchical model, a child record type can only be connected to one parent record type. Finally, multiple set types may be defined between the same record types. CODASYL data models are usually represented using a network or Bachmann diagram. Charles Bachmann was one of the important contributors of the CODASYL model. Here you can see an example. We have 3 record types: department, employee, and project. A department has 0 to n employees. An employee works in minimum 0, maximum 1 department. A department can work on 0 to n projects. A project is assigned to minimum 0, maximum 1 department. As with the hierarchical model, one-to-one relationship types have to be again enforced or modeled in the application programs, which is not nice. N-to-M relationship types need to be also modeled using a workaround. A member record can only belong to one occurrence of a specific set. Hence, we cannot just define a set type between the corresponding record types. One option is to introduce a dummy record type, which is included as a member record type in 2 set types having as owners the record types of the original N-to-M relationship type. This dummy record type can then also contain the attributes of the relationship type, if any. You can see this illustrated here. Suppose we have an N-to-M relationship type between employee and project. In other words, an employee can work on 0 to m projects, whereas a project can be worked upon by 0 to n employees. We model this in CODASYL by introducing a dummy record type, works on, which also includes the attribute type of the relationship, hours worked, representing the number of hours an employee worked on a project. Here you can see this illustrated with some example records. You can see that employee 120 only works on project 10, whereas employee 150 works on projects 15 and 20. It is clear that this implementation of N-to-M relationship types has serious implications for data usage. Suppose we have a query which asks for all projects an employee is working on. To solve this query, we first need to select the set in the set type between employee and works on. For each member record, we then need to determine the owner record in the set type between project and works on. In case another query asks for all employees working on a particular project, then we need to navigate the other way around. Again, this is an example of procedural DML, since we explicitly have to work out a procedure to solve our query by hopping from record to record, or in other words, working with one record at a time. Here you can see the navigation path followed, in case we are interested in finding all projects employee number 110 is working on. CODASYL provides no support for recursive set types or set types with only one participating record type. A dummy record type needs to be introduced, which is then defined as a member in two set types, each having as owner record type the record type of the recursive relationship. Note that this again implies extensive navigation when manipulating the data. Also, no relationship types with more than two participating record types are supported. As we already mentioned, CODASYL allows to logically order the member records of a set. An example ordering could be alphabetically or based upon birth date. This can be useful for data manipulation. For the root member record type, the system can act as the owner, which is then called a singular or system-owned set type, which obviously has only one set occurrence. Here you can see the CODASYL implementation of our HR administration example. The works on dummy record type models the end-to-end relationship type between employee and project. The hierarchy dummy record type implements a recursive relationship type modeling the supervision relationships between employees. Two set types are defined between employee and department. The first one models which employee works in what department, and the second one which employee manages what department. Finally, a set type between department and project models which department works on what project. Here you can see the cardinalities as we ideally would like them to be. The underlined cardinalities cannot be enforced by the CODASYL model. Again, our CODASYL model has some important shortcomings to note. According to our CODASYL model, an employee can be managed by multiple employees, which is not desirable. The model does not allow to enforce that a department must have exactly one manager. It also does not allow to enforce that a department has minimal one employee. All these constraints and rules need to be embedded in the application programs, which is clearly not nice.